and in that to you the most important parameter called as isoparametric representation. See, the isoparametric representation refers to usage of the same shape functions. That is, if you want to find out the displacements, u equal to n1 q1 plus n2 q3 plus n2 n3 q5, or v equal to in the similar manner, you can also find out the corresponding Cartesian coordinates, that is x and y, with the help of the same shape functions. You can derive shape function only once, and by using these shape functions, I can find out the coordinate of a given point. If I know the coordinates of the other three nodes, I can just express it and I can find out that. Suppose in this case, suppose if we use a notation, for example, I will use let xi minus xj. I will represent it as xij. Okay, or even if you want xj minus xi, I will call it as xji. This is the convention if I am using. For example, if you take this x1 minus x3, I would like to write it as x13. Similarly, x2 minus x3 if I want, I will write it as x23, and same as y and all that. So therefore, this can be written as x13 zeta, x23 eta plus x3, and this will be written as y13 zeta plus y23 eta plus y3. So this is the way you can express it. So therefore, with the help of this, I can find out the remaining things. So therefore, if I want to make use of this, on one of the you can say example we will take now. For example, the problem statement says evaluate the shape functions n1, n2 and n3 at the interior point P. Interior point P for the triangular element shown in figure. For the triangular element shown in figure. So let us note on the sketch. See, this is going to be the triangular element which is shown here. This is like this, this is like this, and this is like this. The coordinate of 1 are 1.5 and 2. Coordinate of the node 2 are 7 and 3.5. And coordinate of 3 are going to be 4 and 7. And there is an interior point P whose coordinates are also given to you. So we know the coordinate of that is 3.85. We know this 3.85 and 4.8. These are the x and y value at the point P. And we need to find out the three shape function at this particular point. What will be the shape functions and all that. So let us quickly note down what are these known factors. X we know 3.85. Y we know it is 4.8. Let us go to x1, x2 and x3. y1, y2 and y3. If we know that, let us substitute this. What is x1? x1 is 1.5 and then 7 and then 4. And y1 is 2, 3.5 and 7. These are the, what you can say like this. Since you are already knowing these two relations, what you require is x13. x13, which is nothing but x1 minus x3. It is 1.5 minus 4. It is minus 2.5. x23 if I want, it is x2 minus x3, 7 minus 4, which is 3. Okay, this is about this. Similarly, if I want y13, y13 is given by y1 minus y3, that is 2 minus 7, which is going to be minus 5, and y23 is given by y2 minus y3, that is 3.5 minus 7, that is minus 3.5, you will get this. So once you know these, let us make use of these two relations. Yes, what are those relations? X equal to x13 zeta plus x23 eta plus x3. So obviously it is 3.85 is equal to x13 minus 2.5 zeta plus 3 eta plus x3 is going to be 4. This is that. Then similarly, if I want the second one, that is y equal to y13 zeta plus y23 eta plus y3 if I want. What is the y? Y is going to be 2, which is equal to y13. It is minus 5 zeta minus 3.5 eta plus 7. These are the two important equations. Equation this and this I can find out in terms of the constant and I can rewrite. So if I take it and start writing that, yeah. So let us take this. Once you change these for us here now, it is 2.5 zeta minus 3 eta is equal to 0.15, that is 4 minus 3.85 will be the 0.15. Similarly, on the other side, 5 zeta plus 3.5 eta is equal to 2.2. I will get this. And this, if you want to eliminate, you can multiply by 2, the whole bracket, all this, and then take minus, minus, minus here. And when you evaluate that, what you will get here is minus 9.5 eta equal to minus 1.9 or eta equal to 0.2 you will get. Similarly, if you substitute this in any one of the equation, you will get eta equal to 0.3 you will get. But you are already knowing that n1 is nothing but the zeta itself. So therefore, this is 0.3. And n2 shape function is nothing but eta, that is 0.2. And n3 is nothing but 1 minus zeta minus eta, which is 0.5. So therefore, what we get, the three shape function at this point are 0.3, 0.2 and 0.5. This is the final answer for your problem which is given to us. Okay, the next interesting point is we have to develop a relation for strain displacement matrix and the strain components, how to find out the strain components, and then later on we have to find out the stress within the triangular element. So since it is called as constant strain triangular element, the strain is constant throughout the element, automatically the stress is also constant throughout the element. So let us quickly see, we have seen that U and V, in the last class I have told you, V, U and V, and x and y are the functions of zeta and eta. Functions of zeta and eta. These are the functions. Therefore, I can rewrite u, if I want to write the u of x comma this x comma zeta eta, and y, which is again eta. This is also like this. This is as far as this is. And v is also equal to v of x comma zeta eta, y comma zeta eta. So that means both u and v as well as x and y, that in turn dependent on the zeta and eta. So therefore, we have to make use of the what is called as the chain rule. For example, if I want to write, since the displacement depends on two factors, obviously I have to use partial derivatives. Dou u by dou zeta can be written as dou u by dou x by dou zeta plus dou u by dou y into dou y by dou zeta. This is the first one. Similarly, if I want dou u by dou eta, if I want, it is again a dou u by dou x into dou x by dou eta plus dou u by dou y. This is going to be now, yes, x. This is dou u by dou y by dou eta. So this is how you can write like that. So therefore, if you write in the matrix format, that is dou u by dou zeta, dou u by dou eta. By chance, if you want to write it in the matrix form, see, obviously this will be dou x by dou zeta, dou y by dou zeta, and this is dou x by dou eta and dou y by dou eta, and outside what you will get is dou u by dou x, dou u by dou y. This is what you will get. This square matrix, whatever it is there here, this has got a specific name. This is called as Jacobian of transformation or Jacobian matrix. So therefore, this I can rewrite it as J, the matrix, where J matrix is nothing but Jacobian of transformation. See, this is the J, where it is a 2 by 2 matrix, where 2 by 2 square matrix denoted by J, is called Jacobian of the transformation. Okay, so therefore, if I want to separately write, this is our J is given by dou x by dou zeta, dou x by dou zeta, dou x by dou eta, dou x by dou y by dou zeta, dou y by dou eta. Okay. Now, just to give you one sample, you know that x is equal to x13 zeta, x23 eta plus x3. So naturally, if I take dou x by dou eta, this is going to be x13 only. Similarly, if I want dou x by dou zeta, if I take like this, it will be x23, like this. In the similar fashion, if you derive it to y, you will get a y23 and y13 you will get. So therefore, this can be written in terms of x13, y13, x23, y23. This is what we can write for the Jacobian of transformation. This is a 2 by 2 matrix. Okay, this is the interesting part, what you have to say now. See, but for finding the strains, because you are already aware, what is strain, you can say, you just look back. Strain is given by what? It is given by dou u by dou x, dou v by dou y, dou u by dou y plus dou v by dou x. This is what we know. So therefore, what we want is this. But whereas here, if you look at this, this is the other side. So naturally, to get this, I have to take the inverse of the Jacobian matrix. So therefore, if I want the dou u by dou x, if I want, and dou u by dou y, in case if I want, I have to take the inverse of the matrix. So this is dou u by dou zeta, and this is dou u by dou eta. So this is what you will get. Then what is this inverse of a matrix? Especially for a, what you can say, 2 by 2 matrix. This is given by 1 upon determinant of J. See, always remember these two are getting interchanged. These are going to have only change in sign. So therefore, if you write this, 523 will come here. x13 will come here. That is, they get interchanged. Whereas these two will remain there with a negative sign. That is minus y13 minus x23. This is going to be what is called as the inverse of a Jacobian matrix. And what is the determinant? Determinant is always this cross minus this. That means if I want to write determinant of J, if I want, it is nothing but x13 y23 minus y13 x23. y13 x23. So this is called as the determinant of the Jacobian matrix. So you can find out from that, and you can always write this one. But if you look at the geometrical relations, determinant of J is always given by 2 times area of the triangle. Area of the triangle. Whatever triangular element is there, you have to take the area of that, and that will be the 2 times of that area is nothing but the determinant of J. Or sometimes area itself, if you want, it is half of the modulus of the determinant of J. That is always you have to take the positive value. Area cannot be negative. So therefore, I have to always take the mod of that. What is the meaning I wanted to tell you is, suppose if I have a triangle with 1, 2, 3 as nodes and x1, y1, x2, y2 and all that, the area of the triangle is given by area of the triangle in terms of the Cartesian coordinate EE. If I want, I can write it as half into bracket x1 minus y2 minus y3 plus x2 into y3 minus y1 plus x3 into y1 minus y2. This is the formula to find out if you know all the 3 coordinates of all the 3 nodes, you can find out the area of the triangle by this. And as I told you, determinant of J, if you take half of this, is exactly equal to the area of the triangle. If you want the area of the triangle, it is going to be half of the determinant of J. That we will see, because we have already worked out on one of the problem where we will just check how to find out the area as well as we will find out the triangle, Jacobian and inverse of the Jacobian and everything we can find out that. Okay. So we will take the same last example only. So if I write the Jacobian, what will be that? Tell me. Jacobian matrix, what we had taken there, it was x13, x23, y13, y23. Correct? No, this is not that. This is x13, y13, x23, y23. This is the Jacobian matrix. Since you are already knowing those values for that earlier problem on the triangle, tell me how much it is. x13 was minus 2.5 and this was minus 5. This was 3. This was minus 3.5. This was the Jacobian of the matrix. And what is the determinant of J? Determinant of J was, tell me. Let us make use of that. That is x1 and x2 and all that, or we will cross check this. That is x13, y23 minus x23, y13. So this is nothing but x13, that is minus 2.5, y23, that is minus 3.5, minus x23, that is 3, and y13, that is minus 5. If you do that, altogether the answer is going to come 23.75 units. 23.75 units. This is the answer. You are going to get this. Okay. This you can very well cross check, because this is going to be half of the area. So let us find out the area of the triangle. What is the area of the triangle? If you multiply by 2, you should get the same answer. I have already given you. It is half. X is 1.5. Y2 minus Y3, that is 3.5 minus 7, plus X2, that is 7, 7 minus 2, plus 4 into bracket 2 minus 3.5. So if you do this, the area comes out to be, actually literally it will come half of the 23.85 you will get. See, look here, this is we are already knowing that your determinant of J is 2 times area. If I multiply by 2, 23.85, and almost very much closer to this answer, we are going to get that. So that means it is confirmed that the area of the triangle, when you multiply by 2, it will be always equal to the, what you call it as, the determinant of J. So this is what we have derived now. Now let us go for, see, one interesting point you have to remember, if these nodes 1, 2, 3, if they are given in anti-clockwise direction, then only the area and Jacobian comes positive. By chance, if you give it in the negative sense, then that is in the clockwise direction, if you go for giving the numbers like 1, 2, 3, 4 like this, if you give, then the determinant becomes negative. So to avoid that, always when you are giving the node in the anti-clockwise direction, this is the important discretization. Okay. Now let us go to the next part of this. Where we had come, finding the dou u, dou x we were finding. Okay. Now let us quickly go to the dou u by dou x. What was there here? Matrix dou u by, okay. If I open this, what will happen? This will be outside. This will be there. If you look at this, it is y23 dou u by dou zeta minus y13 dou u by dou eta. And similarly, if you go below, minus x23 dou u by dou zeta plus x13 dou u by dou eta. So this is going to be what I got of this. So in this way, since you know this, directly you can similarly, you can write for dou v by dou x and dou v by dou y also you can write. What are those, tell me? This will remain same. 1 upon determinant of J will remain same. This again it will be remaining same. Y23. This will remain same. Only dou v by dou zeta minus y13 dou v by dou eta will come. Here it is minus x23 dou v by dou zeta plus x13 dou v by dou eta you will get. So once you know all these 4 components, then it is very simple for us to write down the strain matrix. So let us write down that. That is go to now. So using, we know already, using strain displacement relations. Okay, what is this? It says epsilon strain is given by dou u by dou x, dou u by dou v by dou y, dou u by dou y plus dou v by dou x. See, this is nothing but the normal strains. These two are normal strain, and this is the shear strain. Okay, gamma xy, epsilon x, epsilon y, and gamma xy are the two normal strains and one shear strain. So if I open this, what will happen? Just tell me. This will be 1 upon determinant of j will be always there. Okay, dou u by dou x. Where is dou u by dou x? Yes, this is our dou u by dou x. So therefore, I will write y23. But interestingly, you are already knowing what is u. Tell me. U is we have seen it is in the earlier class q1 minus q5 zeta plus q3 minus q5 eta plus q5. So therefore, if I want dou u by dou zeta, okay, this will be always equal to q1 minus q5. And similarly, if you want dou u by dou eta, it is q3 minus q5. Correct? Similarly, if you want v, it is q2 minus q6 zeta plus q4 minus q6 eta plus q6. Okay. So similarly, here also you can write dou v by dou zeta. If I want, it is q2 minus q6. And if I want dou v by dou eta, this. So obviously, if I come here, what will happen? What will be always okay. Then dou u by dou zeta, it is q1 minus q5. I will substitute q1 minus q5 minus y13 into dou zeta is q3 minus q5. Correct? Correct. q3 minus q5. Okay. Which one? x23. Dou u by dou zeta is again q3. This is not zeta. The second one is dou v by dou y. So dou v by dou zeta is q2 minus q6 x plus x1. I would like to write something interesting here. Or you can interchange the relations. This is possible only at this point. Similarly, you can this form also. So if I substitute such type of things in the above equations, what I will get? Let us see that. Define it here. If I substitute in the strain, what I will get? Will be written as 1 upon determinant of J will be remaining here, Y23 Q1 plus 31 Q3 plus Y12 Q5 X32 Q5 plus Q2 X13 Q4 X21 X23 X3 Q3 3. So once you substitute, please remember this is a 6 by 1 matrix. What is this B? This, so how to define that? That will be the to be called as the B matrix. Of course, so therefore this strain is always expressed as the all these are coordinates only, constants. Everything is constant. And Q1, Q2, they are also numbers only. So therefore, in all, what I am trying to say is the product of B into Q is nothing but a constant only. That is the reason why we say this triangle is called constant strain triangular element, because the strain does not contain any zeta or eta term. So therefore, the stress or strain is going to be throughout constant throughout the element. That is the main beauty of this particular element. So therefore, this elemental this information is there. Put it for every element again. So now let us please take one simple example how to find out this B matrix. I want to calculate the stresses and other matrix. No problem. Let us quickly see that. Let us take one square certain point T. Let me write anticlockwise 3. This is the width of height of this is 3 mm of this, and you have to write down the coordinate of this. This is 1. See, as far as 1 origin, what we are going to get this. Now, since if we look at the B matrix just now, what we need is we need x2 1, x3 2, x1 3, all this we need, and y1 2, y2 3, and y3 1. We require this. 1 is x2 minus x1, it is coming 0. y2 3 or y2 3 is coming 2. y3 1 is coming 0. And again, similarly x3 2 is coming to be minus 3. So once you know all these values, find out the determinant now. Determinant of J, if I want to find out, it is, what is this? x1 3, y2 3, minus x2 3, y1 3. Look at this figure, this is 3, this is 2, minus 3 into 0. If you look at coordinates, these are the same. So automatically that is 0 means. So therefore, if I want to write the this will come to 0, minus 3, 0, minus 3, 0, 0, 0, 3, 0. Minus 2. Exactly you are going to get as a B matrix once you find out all these elements for this, and this is needed for that. And of course, if you want to find out the strain matrix for the first element epsilon 1, it needs to be multiplied by q1, q2, q3 of that particular node. Second element, like element number 2 we'll write. Element number 2. See here what happens is your x1, x2, and x3. Currently here now. y1, y2, because the node numbering. So now look at this. What is our x1? x1 is 0 and 2, correct? And 2 is again 0, 0 for the second element. And 3 is going to be 3 and in the similar manner you can go on finding. all these elements. First work out and keep it ready so that directly I can write out the result. So similarly, in a similar manner, if you want determinant of J, okay, what is x13? X13 is minus 3. Okay, then y, y23 is going to be minus what is that, x2, yes, x23, x3 only, because x32 is, and lastly y13, y31 are 0 only. So this indicates that again, once again, determinant is 6 only. For this second element also, the determinant is going to be 6 only. So therefore, if I surprisingly, if you see exactly opposite, positive, it will become negative here. Whatever negative is there, that will become positive here. 0 minus 0, 0 minus 3. 0 minus 3 because it and 0, 0. What you can say, B matrix. First you write the B matrix. With the help of this you can calculate strain and stress. You will have to calculate. Later on now I am going to show you how to find out the element stiffness matrix. In that case again you will be requiring this B matrix will come there, and using this B matrix first you have to develop the element stiffness matrix for every element number 1, 2, 3, 4 like that, then make the global assembly and then solve for the displacements of all the nodes which are associated with that. So for that we will be going for what is called as potential element stiffness. What is called as potential energy concept. Potential energy approach. What is this? What is knowing? Element potential energy is given by pi E. And this is strain energy plus potential. Okay. If I want to an element over the volume, sigma transpose epsilon dV versus E transpose dV minus Q transpose UI PI. This is what we have seen in the case of this. Now let us quickly go for this. Sigma is nothing but epsilon into Young's modulus. See here the question, most important part is since sigma, it's because for a 2D element, there is no meaning. It is always going to be a vector of 3 by 1, 2 normal stresses. sigma for a plane strain, it is called C epsilon. And I have already told you what are the values. So therefore, if you come here, sigma is given by B Q into C. This is what we know. If I take sigma transpose, see this is equal to Q transpose B transpose into C. C is symmetric, so therefore there is no question of transposing. It is one and the same, it will remain C only. So therefore C transpose will remain. So if we substitute in this, let us, this is going to be is T into dA. See, this is the what, and you know V. And of course, you know so therefore this meaning of this and say directly we get the components in addition to that, we're going to get that. This is as far as what it is at L level. Same equation for the global, so I need to sum up or sign and you have to in state energies, individual force elements, everything you have to. So therefore, the total potential energy of the system or the structure, if I want, it is total pi is given by summation of the element of integration epsilon transpose C epsilon into T into minus summation over the element U transpose F into T into dA minus summation over the elements U transpose T into dl minus Qi Pi. Right. Or you, that is also not a problem. Ui transpose P. So this represents, this part is nothing but the strain energy. Please remember. Of the strain energy. This from this part, one can develop the element stiffness matrix. You can just go on developing this, and you can get that. Okay, I think as I told you, write down the element stiffness matrix. How to stiffness matrix? Yeah. Just now I told and what we do. Let us yes. And epsilon is nothing but and this is what are the other constants? Right. But you are already area of the total element only. AE is the total area of this element, and that is what exactly you are going to get that. So this equation, yeah, E is nothing but the element stiffness matrix. So therefore, if Ke as my element stiffness matrix, there are no integration terms, so nothing is there. Directly it is a simple multiplication of all these things like. So if you go on adding, this is the total potential energy of the end. And if you differentiate this, so once you put the proper condition into this equation, one can solve the equation and get the, you can say, nodal. What are the properties of this? It is a square matrix. 3 by 3, 10 by 10, 15, 15, like it is going to be a square matrix. It is going to be symmetric matrix. If you draw the diagram, whatever is there in the upper triangle and lower triangle, they are one and the same. That is why global stiffness matrix is a symmetric matrix. Then it is banded, or it is called as banded matrix, or it is also called as what you can say banded. It is actually sparse matrix, banded or sparse. That is the name which are banded means it is to minimize the what you can say spaces which are available for the computer. We should occupy minimum spaces for the locations. If you look at global stiffness matrix, there are a number of zeros which to save, you can say storing these empty spaces. We are going to make this as a branded, and we want to the semi bandwidth of this particular stiffness matrix, global stiffness matrix. Let us see what is the formula which is used for finding the on that. Bandwidth. That is the number of slots which are available to store the system matrix. Now, let us say this is like, let us say this is I1. For every element, these are the global node numbers. You can say. Of it is positive or negative. Like that. You take the maximum of the first one. Called as the semi bandwidth. So maybe I can show you for we have taken that here. Now, for example, if I take this and if I don't give the anti 3, 4, to call this as number, and you name take any one of them. So naturally, for the first one, maximum difference between the known numbers for the first element, you can say that is maximum. Correct or not? Similarly, for the second element, but when you go on finding the value of maximum differences among